Okay, so today we will now discuss the common mode rejection ratio. Now the full form of common mode CMRR, it is the abbreviated term is CMRR. The full form is common mode rejection ratio. Now before understanding the common mode rejection ratio, first talk about the differential amplifier. Now in the case of the operational amplifier, we have talked about the differential amplifier. Now suppose the differential amplifier, the block diagram of differential amplifier is something like this. Input voltages is V1 and V2 and output voltages is V0. So suppose this is an differential amplifier. Now assuming that it is formed by a linear active device, it is an ideal one. And if the analysis of a differential amplifier, a difference amplifier can be defined as an ideal one if any signal which is common to both the inputs has no effect on the output voltage. So I am again repeating, a difference amplifier can be defined as an ideal one if any signal, okay, if any signal, ideal one, if any signal common to both input, if any signal common to both input has no effect on output. Now just understand this term, okay. So if any signal common to both the input has no effect onto the output, so that is called the ideal differential amplifier. Now in the case of the differential amplifier, is the gain is AD, so the output voltage can be written as AD into V1 minus V2. So this is the expression for the AD is the gain of the differential amplifier. Now the input voltage, now if the input voltage V1 is equal to the input voltage V2, now what will be the output voltage? The output voltage is actually 0 volt. Okay, why it is 0 volt? Because the signal common to both the input get cancelled, because this signal is V1 is given to input terminal and V2 is given to another input terminal. Both this is equal, that means both the signal common to both the inputs is get cancels and generates the zero output voltage. Now this is only possible for an ideal operational amplifier, but the practical difference amplifier does not follow the above equation, as the output voltage not only depends on the difference signal V0 but depends on the average voltage. That means the output voltage in the practical difference amplifier, the output voltage does not depend on this difference signal but also depends on the average signal. Now the average signal is represented by V1 plus V2 divided by 2. Now what do you mean by that? That means in the case of the practical amplifier or the practical difference amplifier, if the input of one terminal is 200, suppose one terminal is 200 microvolt and another terminal is 100 microvolt, okay, so the difference between these two signal is 100 microvolt. Now consider another difference amplifier in which the same difference amplifier where the input is 1000 microvolt and the input is 900 microvolt. Now what happened? The difference between these two input is same 100 microvolt, okay, but the output is not the same. In the case of this, if we just take a practical example or practically we take the output for both these cases, then we can see that in the case of the practical operational amplifier, the output voltage for these two cases would not be same. So that means the output voltage is not only depends on the difference signal but also depends on some another signal, and that signal is called the common mode signal. So this is the average signal or called the common mode signal. Now in the case of the practical understanding, the common mode signal is the noise signal. It is practically the noise signal. So noise should be cancelled, that is common to both the signal. So the ideal operational amplifier should cancel the noise, that means noise has no effect on the output, but the practical differential amplifier or the operational amplifier cannot attenuate the noise completely, but it should be desirable that SNR should be high. Now what do you mean by the SNR should be? So noise is an example which is called the common mode signal. So this is an example of the common mode signal which must be eliminated but cannot be eliminated completely in the case of the practical operational amplifier. Now in the case of any amplifier, SNR should be high. What do you mean by the SNR? SNR is means signal to noise ratio. That means we want any kind of amplifier or any kind of device, that means signal strength should be high and noise strength should be low. That means the SNR, if SNR is high, signal strength should be high and noise should be low. So noise must be attenuated at the input, okay, so that it has no effect or very minimum effect at the output. So I hope you are clear with this concept, that what is the difference signal, that in the case of the ideal difference amplifier this is the expression, but the practical difference amplifier this is not the actual expression, because experimentally when we did the experiment we have seen that if the this input 200 and 100, though the difference is 100 microvolt, the output is another. And in this example, if the difference is still 100 microvolt, output should be same with this, but actually it is not same with this, because the output of this output voltage expression does not depends on this difference voltage but also another voltage, that is called the common mode voltage, and practically the common mode voltage is the noise voltage, okay. So you can think of another equation, that means V0 should be this AD into VD that we have studied till now, but that is not the case. It is also depends on the common mode signal. So this is your common mode gain and this is your common mode voltage. So this is the expression for the practical difference amplifier. So VD is the differential input voltage. This is VD. VD is the differential input voltage, that is V1 minus V2, and VCM, that is the common mode voltage, that is the average voltage, that is average voltage is V1 plus V2 divided by 2. So this is the expression for the practical operational amplifier, and AD is the differential gain. This AD is the differential gain and ACM is the common mode gain. So till now we have studied only this equation ideally, but practically this is the actual equation. The operational amplifier output depends on this equation. Hope it is clear to you. So the CMRR should be defined as a ratio between AD divided by ACM. So for the good operational amplifier, the CMRR should be as high as possible. That means the difference mode gain should be as high and common mode gain should be as low as possible. Okay, so that is the desirable condition. Now CMRR can also be expressed in terms of dB. Now if we express the CMRR in terms of dB, so it should be AD divided by ACM. Okay, so this is another expression for the CMRR. So this is the two expression for the CMRR. CMRR is the ratio between the difference mode gain to the common mode gain, and for a good operational amplifier or the good difference amplifier, this difference mode gain should be as high as possible and the common mode gain should be as low as possible, because the common mode gain is nothing but the noise signal, so it does not want noise signal gain should be high. So if it is so, then our signal strength is low at the output. Okay, so we have also studied this equation, that V0 is A1 into V1 plus A2 into V2. This equation we have also studied, and where V1 is nothing but okay, so VD is, we know VD is V1 minus V2. Okay. VD is V1 minus V2 and VCM is V1 plus V2 divided by 2. Okay, so VD by 2, if we just VD by 2 is equal to V1 by 2 minus V2 by 2. Okay, so from that if we just simplify this, your V1 comes out to be, from these two equation your V1 comes out to be, okay, this equation and this equation, your V1 is comes out to be VCM plus VD divided by 2. Okay, this is your V1. Just get these two expression. Okay, and V2 is nothing but VCM minus VD divided by 2. So this is the two expression for V1 and V2. Okay, get from these two equation. Next, we also studied the expression this V0, this expression. From this expression V0 I am just replacing V1. So V1 is nothing but VCM plus VD divided by 2 plus A2 into VCM minus VD divided by 2. So this is the two expression, and if we just get common, just rearrange this equation. So this is VCM, okay, A1 plus A2 plus VD A1 minus A2 divided by 2. Okay, so just comparing this equation with the another equation that we have also studied, that V0 can also be represented as VCM into ACM plus VD into AD. So just comparing these two, your ACM will be A1 plus A2 and AD will be A1 minus A2 divided by 2. Okay, so this is the just comparing these two equations. Okay, so ACM comes out to be A1 plus A2 and AD comes out to be A1 minus A2 by 2. So we have previously we have written that the CMRR is equal to AD divided by ACM. So this comes out to be A1 minus A2 divided by 2 into A1 plus A2. Okay, so just replacing these two, that AD is equal to A1 minus A2 by 2 and ACM equals to A1 by A2. So this is the expression for the CMRR. Now in the practical ideal case, ACM should be as low as possible. That means CMRR should be as high as possible for a good operational amplifier. Now from this expression you might wonder that the numerator is difference between the A1 and A2 and the denominator is the summation of A1 plus A2. So how the CMRR should be high in this case? Okay, so one thing you must remember, that whenever we have written the expression for V0, that means you just think in this way, that this A1 and A2 is the gain of these two input. That means in the case of the operational amplifier, one input is positive, one input is negative. Okay, so the gain of this expression V0 equals to A1 V1 plus A2 V2. Okay, so this is nothing but that A1 equal to V0 divided by V1 when V2 equal to 0 and vice versa. So this gain A1 and this gain A2 has the inverse relationship. That means A1 and A2 has opposite sign. Okay, so as these two are opposite sign, then this difference become positive and this summation becomes negative. So eventually the CMRR should be high. So that is the case. So you must understand this. That means that this is the gain of one terminal, this is the gain of another terminal. So these two gain, that means if the input is connected to this terminal, gain is negative. If the input is connected to this terminal, gain is positive. So this gain A1 and A2 are the opposite sign. As this is two are the opposite sign, and these two difference become positive and these two summation becomes negative. That means CMRR itself is high. So for the good operational amplifier, CMRR should be infinite. Ideal case, but the practical case, CMRR should be high, and CMRR should be high came from this equation. It will be very much clear that CMRR is very much high. So this is all about the concept of CMRR. Thank you. So after the discussion of the CMRR, we now discuss the importance of the slew rate. Now slew rate is another important characteristics of the specification of the op amp. Slew rate. Okay, so slew rate is defined as the maximum rate of change of output voltage per unit time. Okay, so it is the max allowable rate of change of output voltage with time. So this is the totally theoretical definition. Okay, and slew rate, as the definition said, it is defined as dv0 by dt. Okay, so this is the max, dv0 by dt max, and its unit is volt per microsecond. Okay, so slew rate is the maximum allowable rate of change of output voltage with respect to time, and it is represented by mathematically as dv0 divided by dt max, and unit is volt per microsecond. So this is a very important parameter for high frequency applications such as oscillators, comparators, filters, etc. Typical values of the slew rate of IC741 is 0.5 microvolt, volt per microsecond. Typical value is 0.5 volt per microsecond for IC741 operational amplifier. Now the slew rate indicate how rapidly a operational amplifier can vary its response to variation in the input frequency. So I will draw a diagram so that you can get a feeling how what is actually a slew rate. Now, I am saying whatever I am saying till now, it is just a definition. So just see the diagram, you will get a feel how the slew rate is actually look like. So these changes in the voltage gain, normally the slew rate of the operational amplifier is fixed. If the slope requirement of the output signal are greater than the slew rate, the output will be obviously distorted. Therefore the slew rate is a very important factor to select the operational amplifier in high frequency application. Now in the voltage follower circuit, the input of the large amplitude and the high frequency sine wave. Okay, so mathematical expression for the slew rate: assume the supply voltage Vs is equal to Vm sin omega t or sin 2 pi ft, whatever may be. So time sin 2 pi ft. So this is your supply voltages. Then the output voltages is nothing but, okay, so this is your Vd. So output voltage is your A into Vd. So A into Vm into sin 2 pi ft. Okay, so dv0 by dt max, dv0 by dt max is nothing but your slew rate, and that is equal to A into Vm into sin 2 pi f, and next term is sin 2 pi ft. Okay, so as we are considering dv0 by dt max, d by 0 dt max, the max value of this is 1, so the slew rate is nothing but this term. Okay, so slew rate is nothing but this term, A Vm into 2 pi f. Okay, so slew rate is nothing but A Vm into 2 pi f. Okay, this is the slew rate. So all the things I have discussed till now is just the theoretical feel or the theoretical definition of the slew rate. Okay, now what is actually the slew rate? Slew rate, I said in the definition of the slew rate that the slew rate indicates how rapidly operational amplifier can vary in response to variation of the input frequency. Now suppose your input signal, in the case of the square wave, you can get a feel if you practically do a practical of the slew rate, then you can see this kind of waveform. That means this is a ideal square wave. Okay, this will be not bent like this will be the straight line. So I am again redrawing the circuit. So this will be straight line like this. Okay, like this. So now you can see what happens. The output signal, this is in the 0 time, this is coming from high to low. So this is a plus B and this is your minus B. So from the plus B to minus B, it comes in no time, but theoretically this is not going to happen. So what happens now is that this is the signal, and now it comes out to be like this. Okay, so this is the case. That means it takes some finite amount of time to get to the negative level. So this is the dv0 and this is your dt. This is your dt and this is your dv0. Okay, so theoretically from the plus v to minus b, it takes no amount of time to get from plus b to minus b, but practically what happens, it is not the case like this, it is the case like this. So this time is dt and this voltage is dv0. Now how fast to given this input, suppose the input is given this, and how fast the operational amplifier can track its response with respect to the operational amplifier can vary its response to the variation of the input frequency, that actually measures the slew rate. So slew rate is obviously the specification of the slew rate. You can see that the slew rate is high is a very good criteria. Okay, so this is all about the slew rate. So I want you just study on your own so that you can get not the theoretical definition of the slew rate. You can this is the all about the theoretical or the mathematical expression of the slew rate. Just don't go for this. You just get a practical understanding of the slew rate, that what is the slew rate, how the frequency, that if the frequency is very high, then it comes to picture of the slew rate. Okay, and this is the practical case, that the practically it is not like happening like this. Practically it takes some finite amount of time to response of the operational amplifier. So this is the case of the slew rate and why the slew rate is important. Okay, so as the slew rate is higher, it is a very good operational amplifier. So this is all about the CMRR and the slew rate, and I advise you to follow some of the numerical problem based on this, and this will clear your understanding far more better. Thank you.